All right, hello everyone. Welcome to Math 261, 24th. Feel like it's been forever since we got to hang out since we had a break last week due to the holiday. I saw that several of you have gone ahead and started working on your My Math Lab homework, which was a great idea because you are going to have 3 assigned today since we will finish all 3 of these sections. We'll also start 1.4. Remember, we basically did almost all of 1.1 and 1.2 last time. So again, that was great that most of you got a head start. Those of you that didn't, just make sure that you do complete these as much as possible. Aim for A's, aim for B's, whatever you want to aim for, but let's not get F's. So that's going to be due on the 31st. And remember, all due dates have a due time of 11:59 p.m. I'll make sure I say that the first couple of weeks at least. So again, homework will be assigned and due 1 week later. You'll always get at least a week's notice for tests, and I'll try and give you a little more notice when possible. You'll always get reviews for those. And remember, before you can start any of those homeworks, you have to do the skills check quiz first. And what that will do for you is maybe take away a few homework problems that you don't have to, so you won't have to do them because it thinks you've already done a great job. And if it does take them away, you can still go back and hit similar exercise. You'll retain your credit for the problem, but that would still give you an opportunity to practice. So we're going to pick up exactly where we left off last time. We had introduced the idea of a limit. We've talked about how you are approaching from one side. It needs to be the same as approaching from the other. It doesn't necessarily have to be the exact value at that position. Like the limit doesn't have to be the function value, and that makes for really fun cases in the future. And we saw some examples where we were, plugging in things like 4.1, 4.01, 4.001, 4.0001. And then we saw some examples where we just went straight to plugging it in because they were simple functions like linear functions or quadratic functions, polynomials, whatever. And we finished with a radical, which because that has a discontinuity, it's possible that just because you evaluate the function and you get an answer, that doesn't mean that the limit exists. And that particular limit, the left-sided limit, did not exist. The right-sided limit did. And that's because we were at the discontinuity point. So again, we're going to pick up exactly where we left off, talking about limits. So just a little bit more from 1.1 and 1.2, and then we'll dive right into 1.3. We'll make sure we take a break in about 80 minutes, roughly 75 minutes, something like that. Remember, breaks will be 10 minutes. You can stretch your legs. Just make sure you come back in time because we'll just keep on trucking at that point. All right, let's go. Okay, so we had some examples where we were able just to plug in the numbers and get the limit, and I didn't box up the last one. Let's go back to this one, example 2. We're going to do example 2 again, but instead of graphing, we're going to do it algebraically. We're going to call it example 4. Find the limit as x approaches -2, and our function is x plus 2 over x squared minus 4. So again, and we're going to do this algebraically. So try plugging it in. And we get -2 plus 2 in the top over -2 squared minus 4 in the bottom. Please make sure you know how to square negatives in this course. Simple arithmetic mistakes are unacceptable at this level. -2 plus 2 is 0. -2 squared is +4. 4 minus 4 is 0. And this number doesn't exist. 0 divided by 0, we can't divide by 0. So this is an indeterminate form. So when this happens, it doesn't say that you can't do it this way. Oh no. I'm just gonna have to go down here. I'll write it here. When this happens, I can't type in this spot, unfortunately, but I want it on the same page. When this happens, try simplifying the original function. Often simplifying means to reduce. So let's go back to the original problem. The limit as x approaches -2 for x plus 2 over x minus 2. That's not right. Sorry, I'm a step ahead in my head. X squared minus 4. So this would be the limit. And yes, you do have to keep writing this every time in your work. It's tedious. Of x plus 2 over, well, the bottom's factorable. So factoring is often helpful, and that's a difference of squares. I've already told you that you have to be kings and queens of factoring. I gave you some worksheets and website links and everything in Canvas to help you with that if you're rusty. There's always Purple Math and Khan Academy. There's some practice problems and your review homework. But again, you're supposed to know this. So this becomes x plus 2 times x minus 2. That formula is a squared minus b squared equals a plus b times a minus b. And when you do this, you end up with matching factors top and bottom. And this is very often what makes this indeterminate form become, well, determinate. So now what we have is the limit as x approaches -2. With the top gone, that's now just a 1 over. The bottom is now just an x minus 2. And when you see something drastically change like this, now try plugging in again. So this would be equal to 1 over -2 minus 2, which is -1/4. And seeing this negative, I realized that I forgot to write my negative earlier. No, I didn't. I lied. I thought I made a mistake and I didn't. Look at that though. So the limit as x approaches -2 for x plus 2 over x squared minus 4 is equal to -1/4, the same answer we got graphically earlier. But you can't do it right out of the gate because there's a common factor top and bottom that when we plug the number into that common factor, it makes both of them 0 and it gives you something that's indeterminate. Now, if it's just 0 in the bottom, you can potentially say the limit's infinity or negative infinity. It's when you get this that you absolutely had to have reduced it to then get the real answer if it exists. So be on the lookout for that. And that's one of my favorite types of problems to give because it makes sure that you know how to factor. It makes sure that you're paying attention to processes and it makes sure that you're practicing. So let's do a couple more of these. How are we on time? 12:03. B. The limit as x approaches 6 for x squared minus 12x plus 36 over x squared minus 36. So I'm going to go ahead and tell you if you plug in 6 into this problem, I'm not going to show the work. The top and the bottom will both be 0. In the bottom, 6 squared is 36. 36 minus 36 is 0. In the top, 6 squared is 36. That 36 at the end is going to add and make it 72. 12 times 6 is 72, so that's a -72. You have +72 and -72, and they cancel, you get 0 over 0. So you must simplify first. If you're trying to plug in the 6 because it would make the top and bottom 0. Now here's the thing, if I said what's the limit as you approach 5, you could plug it in now. If I said what's the limit as you approach 12, you could plug it in now. If I said what's the limit as you approach 0, you could plug it in now. It's only when that number being plugged in makes the top and bottom 0 that you have to try and simplify it first. because I'm not guaranteeing that this simplifying canceling thing always happens. I could change this to a 5, it's a completely different problem. I can change this to a negative 2 million, completely different problem. So we go equals limit as x approaches 6. So x squared minus 12x plus 36. We're trying to find a pair of numbers that multiplies as 36 but adds to 12. Well, 6 and 6. So we go x 6, x 6. But these 6's have to multiply to positive 36 and combine to a negative 12, so they both need to be negative. If you are not great with your arithmetic with signed numbers, you need to spend 20 hours working on that before next class. Because that's important for factoring, and factoring is never going away in this class. The bottom is another difference of squares, x squared minus 36. That would become x plus 6 times x minus 6. The top and bottom are not the exact same thing. They're close, but one of the signs is different. Now, when you do this, you see that there's a pair of x minus 6's that cancel. There's a top and a bottom. You can't cancel the rest, though, because that's a minus and a plus. They're very close, but you can't cancel that. So this gives us the limit as x approaches 6 of x minus 6 over x plus 6. Now you might be saying, well, I still see all these 6's. This isn't going to work. It makes the top 0. That's fine. As long as it doesn't make the top and bottom 0. That's when it's not fine. So now we'll plug in. So we'll do 6 minus 6. And when you plug it in, that's when you no longer write limit. It's only when you plug in the number that you no longer have to write the limit part. So 6 minus 6 in the top is 0. 6 plus 6 in the bottom is 12. And 0 divided by 12 is 0. So that should be the answer. If you don't trust it, calculator for that quick two-sided approach, parentheses, x squared minus 12x plus 36, close it, divided by parentheses, x squared minus 36, double check everything, looks good. So here's that 6, if I hit trace, let's do like 6.0001. That E says this is in scientific notation with the decimal going left 6 times, that's 0.000008. That's pretty much 0. If I were to plug in 5.99, again, 0.0008, negative. So that's also very close to 0, one on negative, one on positive. So that says it should be 0. Now, if I actually type in 0, look at this. I'm sorry, I'm not supposed to type in 0, I type in 6. It's undefined. It is undefined at the point that we're supposed to be approaching because it's another hole. It's a hole because of the cancel factors. But even though there's a hole there, even though the function value doesn't exist, it does have a limit. We are approaching the same number from the left and the right. This is something that happens a lot of the times in the real world. So let's say you have a virus that has spread amongst the population. And eventually it has to infect everybody possible, or at least it has to hit everybody possible, whether they get infection or they're immune. So let's just say there's a flat 300 million people in America. There's more, but let's say there's 300 million people in America. As almost all the population gets affected by this, whether in a very negative manner or a slightly negative manner, or not really any effect at all, as you interact with it, we get closer and closer and closer to a total count of 3 million. But it's really unlikely that every single person absolutely would get interacted with, because we have people that live in caves and they'll stay in there for 1 year, 5 years, or people that live in the forest, and they exist, but we'll never actually be able to hit that cap because they don't interact with the people who are spreading it. So while that number of 300 million would never be hit, we're basically saying the limit as we keep going on and on and on is that everybody will be affected. So the limit is 3 million, even though we've never really hit it. It's kind of like an asymptote. It's another idea for an asymptote. In fact, we can go to infinities, and that's basically what we're leading up to. So over here at the -6, though, That's a vertical asymptote because that factor did not cancel, so it's not a whole, it's an asymptote. All right, C. Let's do another. The limit as we approach 1 of x cubed minus 1 over x minus 1. Now that top is not a difference of squares, it's a difference of cubes. And if you plug in 1 now, 1 minus 1 is 0, 1 minus 1 is 0, top and bottom, it's indeterminate. You have to simplify first. So this will be the limit as x approaches 1. Now in that document I gave you on Canvas, this formula is up there when we talk about SOAP for the difference in sum of cubes. So your a here is x, your b is 1. So we go a, b, then a squared, a times b, x times 1 is 1x. I'll write the 1 for simplicity's sake here. And then b squared, 1 squared is 1. So again, this is the sum or difference of cubes formula. It's always a squared, ab, b squared. Then the signs, I'll do in color. I will remind us of this. I said for cubes, you can use SOAP. Same, opposite, always positive. So the same means the first sign is the same as the original. Since this is a minus, this is a minus. The next is opposite of that, so a plus. The last is AP, always positive. This is for the sum and difference of cubes only. It has nothing to do with difference of squares. It has nothing to do with trinomials. The bottom is still just our x minus 1. And look at that. You have matching factors, top and bottom, that'll cancel. Boom, boom, gone. So this is now just the limit as x approaches 1 of x squared plus x plus 1. We're going to plug it in. So we get 1 squared plus 1 plus 1, which is 1 plus 1 plus 1, which is 3. So that's our limit. Per usual, if you don't trust it, let's do the graph. Parentheses, x cubed. Oops, why did I do that there? Minus 1 divided by parentheses, x minus 1. You okay, buddy? Sorry, my dog's got a cough. So there's our graph. It actually looks like a parabola, and that's because of the canceling. And when you cancel it, you do end up with a quadratic. But this function still has to have all the same behavior because there's a hole at positive 1 due to the canceling. You can't plug 1 into this. Yes, a polynomial, it's perfectly okay to plug 1 in, which we did, and we got the 3. But this function is ill-behaved at 1 because there's a hole because of the canceling. This is truly what we're analyzing, the fraction part. But for a limiting process, we can simplify it and then plug it in. So if I hit trace, if I type 1, it's blank because there's a hole. But if I type 1.0001, the approach, we get 3.0003. If I do 0.999, we get 2.997. So that's pretty close to 3. Our answer makes sense. It works. And if I haven't said, if you have any questions while I'm talking, please feel free to type those in the chat. I know I don't really like the mics going during class, but I'm absolutely fine with you asking questions in chat. I would never discourage questions. And you can also ask later in email. You can go to the YouTube video and say, hey, at timestamp 35 minutes, 17 seconds, what did you mean by this? If you do comment, if you need me to go to the video, please mention roughly at what time it is, so I don't spend 30 minutes hunting down the particular issue. You can also reference an example that would be able to get me there quickly too. All right, let's go back to the graphical approach, but let's do a piecewise function, and we're going to say, does the limit exist? And this is going to be the limit as x approaches 7 for f of x. And we're going to do it based on a graph, which I will paint as best of a picture as I can. Sorry for the crooked axes. It takes way too long to do this. Otherwise, we're going to have a curve kind of come up like this. We'll have a shaded closed circle for the end. We'll have an arrow on the left. And then we'll have an open circle here. And then from there it goes up. Let's label some numbers. This x value is 7. The open circle has a height of 10. And it might not look even, but this should be a 20. So we want to know, does this limit exist? Now, I don't give you the function, and this is the function. It's this curve until you hit 7, and then it's this curve after that, where you include the left side function, but not the right side. You cannot shade both of these. You can open circle both of these, but you cannot have these both closed because then it wouldn't be a function. I'm going to do something that I can't have for just a second. If I have these both shaded, it would fail the vertical line test. That fails it. Oh man, I hate when I do this. There we go, perfect. All right, so the left-sided limit, we're coming from across this top one, so we're approaching this way until we hit 7. And as we approach it, we seem to be hitting a height of 20. So the left-sided limit, the limit as we approach 7 from the left of this graph, this function, which I did not actually give you, just the picture is what it was given, seems to be the height of 20, because this point has a height of 20. And the function does take on 20 at that. F of 7 is 20. The limit from the left is 20. But check this out. The limit as we approach from the right. So now we're going this way. We're approaching from the right, 7.2, 7.1, 7.01. We're approaching a height of 10. Now that is not the actual function value. The 20 was the actual function value. The limit from the left is 20. The limit from the right is 10. These do not match. Because they do not match, the limit as x approaches 7 of this function does not exist because it's 20 from the left and it's 10 from the right. It's as easy as that. Now, in the real world, maybe you're only worried about the right-sided limit. Maybe you don't even need to worry about the left side of a function. Well, that's fine when you're talking about whatever real-world application you're dealing with, but we're introducing the basics of calculus. Now, you might have a problem that only asks for the left-sided limit. You might have a problem that only asks for the right-sided limit. You might have a problem that asks for the limit. If it asks for the limit, you're worried about both sides. If we give you an algebraic function, maybe you can just plug the number in. Try that. If you get a number, it's probably true. If it's a piecewise defined function, that's another case. If it's a square root function, you have to make sure it's not the furthest left point, or furthest right if the square root's pointing left instead of right, which can be done with a reflection. Okay. So I need more. Oh no, I didn't hit enter enough. This is going to be annoying. If I insert a page, I think it's going to move all that stuff. Yes, it does. All right, in the interest of keeping this organized well, I'm just going to make a new page, a new document. Sorry for that. It's not really an issue. You see it on the screen. We don't have to approach finite numbers. We can also approach positive or negative infinity. When we do this, consider the horizontal asymptotes. Consider the. So this was a topic from Pre-Calc 1 again. Horizontal asymptotes are a height that you approach as you go left forever or as you go right forever. We've seen vertical asymptotes and we've discussed them. We've also seen horizontal asymptotes but didn't discuss them. So Let me just make this a, that's not going to work actually. Yeah, we'll do this. Why did I get a pi? Oh, because I hit second first and I didn't mean to. Just going to change the problem a little bit. So this problem's got a vertical asymptote that we can clearly see right here. The horizontal asymptote is the fact that this thing is kind of flattening out as we go left or right. And that's not even very far. That's just only going to 10. We're talking about when you go to infinity. So back in pre-calc 1, you learned 3 basic rules for horizontal asymptotes. It's based on the degrees. Don't autocorrect me, word. Of the top and bottom. If the degree in the top is bigger, there is no horizontal asymptote, which means no limit at x equals plus or minus infinity. If the degrees, if the degree in the bottom is bigger, the horizontal asymptote is y equals 0, which is the limit. If the degrees are the same, the horizontal asymptote is the ratio of leading coefficients, which is also the limit. So those are the 3 cases for horizontal asymptotes, which are also the 3 cases for finding limits at infinity or negative infinity. And the cool thing is they're not different. The limit at positive infinity for the functions we deal with has to be the same as the limit at negative infinity. I'm not going to say it's the same for every function. And if they're piecewise defined functions, I can't say that. I'm saying for non-piecewise, well-behaved functions, the limit at as you go left forever is the same as the limit as you go right forever. And there are algebraic reasons for that. So let's try this out. Example 6. Find this for A. Find the limit. Let's just say find the limit. For A, we're going to do the limit as x approaches infinity. It would be the same thing if I did negative infinity of 3 over x plus 2. So this is a rational function, and we're approaching positive or negative infinity. So we got to look at the degrees. For the top, the degree is 0. The degree is the exponent of the largest exponent of your x's. There are no x's, which is why it's 0. It's like having an x to the 0 next to the 3. Anything to the 0 is a 1. The degree of the bottom is 1. There's an x to the first right here. I just don't write the 1. No one writes that 1. So the bottom is bigger than the top. So your horizontal asymptote is y equals 0. So the limit as x goes to infinity or even negative infinity of 3 over x plus 2 is equal to 0. That's the answer. And if you don't trust that, let's pull up the graph. 3 divided by parentheses x plus 2. This thing flattens out really, really quickly. This thing is asymptoting really, really quickly. It's getting closer and closer to 0 without ever actually hitting it. Now, if I go to, let's just make the window. Let's make the x maximum 1,000. And let's make the y values just go between -1 and 1. And I still can't even really see this because this is so wide. But if I hit trace, over here at almost 5,000, we're at 6.00 times 10 to the -4, which is 0.0006. And if you keep going right, if you go to a 9,999, that's 0.0003 basically. This thing is getting closer and closer to 0 as you go left or right forever. So again, we're not trying to think about just approaching right here on the x-axis. We're going right as far as we can. That's the drastic difference here of an infinite limit versus the other type of limit, which is a finite limit. B. Let's do the limit as x approaches infinity or negative infinity, doesn't matter. Let's do some weirder numbers. 34x to the 5th minus 12x to the 4th over 16x cubed minus 17x to the 5th. It doesn't matter that there's the same number of terms in the top and the bottom. That's just a coincidence. What is important is that you find the degrees. You got a fraction problem, so that's a rational. For the top, the biggest exponent I see is a 5. For the bottom, now some people will say, oh, it's the 3. It's the first one. That's it. Nope. It's the biggest one. It's actually the 5 here. That's the degree of the bottom. These are the same. So under those 3 cases, if they're the same, the horizontal asymptote is the ratio of the leading coefficients. So the horizontal asymptote is y equals the ratio of leading coefficients. Ratio means fraction. Leading coefficient means the number in front of the variable that has the biggest exponent. So we need the 34 and we need the -17. Don't forget that sign there, the 34 and the -17. Which is y equals -2. So therefore, the limit as x approaches infinity of this goofy function is equal to 2. So maybe this function is dictating the billions of people that are expected to get a certain virus. Again, that's not what I'm saying this is. It's not. Just saying maybe it was. So we would probably never actually hit 2 billion people because the only time we'd hit 2 billion is at infinity, at the eventual number that never actually happens. But within a reasonable amount of time, we would be really, really, really close to that number. We might be at like 1.99 billion or 1.98 billion or 1.97 billion. So we'd be getting closer and closer to that, 1,000 years from now, 10,000 years from now, 100,000 years from now. But in the short term, in just 2 or 3 years, we would get really close to that quicker than you'd imagine. Let's do one more. C, the limit as x approaches infinity. And again, all of these problems are the exact same if it said negative infinity. And let's go with 10x to the 8th plus 7x to the 3rd minus 3 over 4x minus 5. So the degree of the top is 8. The degree of the bottom is 1. The top degree is bigger than the bottom, which under those cases is the third one, or the second one. No, I'm sorry, the first one. The third one that we haven't used. We've seen the first 2 types. This is the third type, which was the first one we wrote. If the degree in the top is bigger, there is no horizontal asymptote. So there is no horizontal asymptote. So the limit does not exist. D and E does not exist. This thing goes to infinity or negative infinity. If you don't believe me, how many times have I said that today? And the point of me teaching you is so that you don't have to keep not believing me and going back to a graphing calculator. You just do it analytically. 10x to the 8th plus 7 x to the third minus 3, close, divided by parentheses, 4x minus 5. Zoom 6. That's a standard zoom. And look at this thing. It doesn't seem to be flattening out in this window. Maybe we're just not in a good window, so let's zoom out. And again, you don't really see this thing flat anywhere. And if you trace it, look, by the time we hit 1.7, we're at 407. 2.5, we're at 3,485. And that's because this top is going to get bigger way, way, way quicker because it's got an x to the 8th and an x to the 3rd. The bottom's only got a linear term. The bigger the exponent, the more it grows. So what happens as we go left or right forever? It's only the leading terms that dictate what happens. As you go to infinity or negative infinity, the leading term, it basically takes over everything. It's not exactly that, but that leading term is going to be so big in comparison to this x to the 3rd term, in comparison to this 3 term, that you might as well just say, hey, it's pretty much this, which is what a limiting process is doing. So basically, you only look at the leading terms. So again, these infinite limits basically only look, limits, only look at the leading terms of polynomials. So it's kind of like, and I'm gonna do this in red just to show you kind of another way to think about this. It's like if with C, this thing is approximately, when you get near infinity, 10x to the 8th over 4x when close to plus or minus infinity. But this 10x to the 8th over 4x reduces to 5 over 2 and an x to the 7th, or 5 halves x to the 7th. And if you plug infinity into x to the 7th, it's infinity. Whereas with B, when you take that infinite limit, you're only looking at the leading terms. You're looking at the first term in the top and the second term in the bottom. So it becomes 34x to the 5th minus 12x to the 4th. Why did I do the minus part? 35x to the 4th over negative 17x to the 5th, which gives us a negative 2 because all the x to the 5th cancels, and that makes a 2. Again, this thing goes to infinity if you plug infinity in, but negative 2 is negative 2. That's why this was the limit. If you do it with A, and I just want to pause there for a second. Obviously, we got negative 2 for the answer in B, but I did forget to write the negative. I was waiting until I pointed it out there to bring it up, but then someone mentioned it. I wanted to go ahead and say that. So make sure for B that your final answer was a negative 2, like it was here, because 34 divided by negative 17 was negative 2. Okay, we had 3 over x plus 2. It just goes to approximately 3 over x. And if you plug infinity, if you think about plugging infinity into the bottom, you've got 3 divided by infinity. 3 divided by the biggest number in the world is the smallest number in the world, 0. If you don't believe me, take 3 and divide it by 1,000, then divide it by 10,000, then divide it by 1,000,000, then 1,000,000,000. 3 divided by 1,000. Small number. Sorry, that was 10. 3, this thing hates multiple clicks. 3 divided by 1,000. Smaller. 3 divided by 1,000,000. Smaller. 0.00003. So as we get to dividing by infinity, this thing just goes to 0. That's the rationalization behind the horizontal asymptote rules, is that the leading terms take over, and then you can actually just ignore them. You don't even need the rules. You can do it like I've done in this red ink. Just imagine yourself only looking at the leading terms, reducing it, and then plugging in infinity. X to the 7th, x to the 6th, x is going to go to infinity. If you have a number, if the x is in the bottom, that's going to turn into 0. If there's no x's, then the answer is the number you have. And that's all there is. All right. Continuity. If a limit exists at a point, it is continuous at that point if and only if, it's a mathematician's favorite phrase, the function value matches the limit. If a limit exists at a point, if a limit exists at a point, then it's continuous, but only if the limit and the function value match. Now we've seen a couple of cases of this that we're kind of describing here. So let's drop some pictures. And again, just sticking in quadrant 1 for the sake of sanity. Going back to this. And we'll have this point right here, C. Then we'll do the same basic shape. But we'll have a hole here. And it's there. Let's put the arrows on all these bad boys. And here we'll have an open circle, and here we'll have a closed circle. Not that it matters which is which. This will be our C. So we're going to say which of these is continuous at x equals C. Well, the first one, this point right here, if you wanted to shade it in, you can. That's the function value. This height, let's say the function values are, I don't know, let's go with D this time. So here we have a D, here we have an E, and a D, and an E. So for the first one, and let's call these capital A, capital B, and capital C. A, the limit from the left is D, the limit from the right is D, and the function value is D. So A is continuous. Because the limit from the left matches the limit from the right, meaning that it has a limit, and the function value is there. The second one, which I'm calling B, is not. Because the limit from the left is the height of D, the limit from the right is the height of D, so the limit does exist. But the function value is up here, not the same thing as the height. So that's because the limit as x approaches C of f of x is not equal to f of C. C is not continuous here because, first of all, the limit doesn't even exist. The left side and the right-sided limits do not match. There's a lot of different cases for continuity at a point. Now, you can also talk about a function being continuous everywhere instead of just at a single point. So, let's just put some numbers in here from 0 to 10. So this thing is continuous at 1, it's continuous at 2, it's continuous at 3, it's continuous at 5, it's continuous at 10, it's continuous everywhere. And that's because to draw this thing, I just put my pen down and I can keep going until the far right side of it. Continuous means you can put your pen to paper and draw the whole thing without lifting it until the end. The middle image, I can put my pen to paper, but at some point I have to lift it to draw this thing up here, which makes it discontinuous. The third one, I can draw the left half, but then I have to lift my pen and put it up here to continue the right part. So that's what it means to be discontinuous. You have to lift your pen or pencil or marker or whatever off your paper, board, or tablet in order to draw it. We can talk about continuity as a whole, as a region, or as a finite point. All right. Example 7. Sorry. Let me go back to black. Let me make sure I've got enough enters hit so I don't goof this up again. Example 7. Let's do another limit. First, and then we'll do a continuity. I actually meant to do this one before. That's my bad. So can we just plug the 5 in? Because there's no way we can reduce this. Can we just plug it in? Well, we'd get 1 over 5 minus 5, which is 1 over 0, which is undefined. Oops, I don't mean to box that. So ... question mark. When you plug it in, you get an undefined value. And you can't reduce it, so algebraically we're stuck. So what you need to do is go to the back to the idea of a left side and a right side approach. And let me just pull out the calculator for that. And I'll say use a left right approach instead. As I said, you can't always just plug the number in. It doesn't always work. 1 divided by x minus 5. So 6. So 5, we see that asymptote. We see that vertical asymptote, which I have not put us on top of yet. This is the first time. The other times it's been at holes. So if you put type 5, oops, you got to hit trace first. 5. It's blank, and that's because there's that vertical asymptote. So let's try 5.01. And we're at 100, maybe 5.001. And we're at 1,000. How about 5.0001? And we're at 10,000. So 5.00001 would be 100,000. You get the idea. So the right-sided limit, we're going up. These are positive numbers. 1,000, 10,000, a million, a billion, a trillion. We're going to positive infinity. So this is the right-sided limit. I'm doing this in a backwards order, not that it matters. So the limit as x approaches 5 from the right of this function is equal to infinity. How about the left-sided limit as we approach 5 from the left for this function 1 over x minus 5? So how about 4.9? Well, we're at negative 10, or is that negative 100? I can't tell because of that little blip there. How about 4.99? We're at negative 100, so the other one was negative 10, and that makes sense. About 4.999? We're at negative 1,000. 4.9999. We're at negative 10,000. So we're still approaching the same number in absolute, but we're going down instead of up. So this one's going towards negative infinity. It's going down forever. You can even see that if you look carefully. From the left, we're going down, 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 down. Then we magically hit the asymptote, which we're not really supposed to touch. And the second we cross over it, we're up here at the top, and we're going down, down, down again. But if you think about yourself approaching from the right, we're heading up to infinity. So the left-sided limit's negative infinity, the right-sided limit's positive infinity. So the limit, since they don't match, the limit as x approaches 5 for 1 over x minus 5 does not exist. Now I need to make a special note here. This is a special important note. If these had both been positive, or let's say had both been the same infinity, I don't want to phrase it any other way. If they were both positive infinity or they were both negative infinity, some people will say that the limit exists and they'll say it's that particular infinity. Some, however, say the limit does not exist because infinity, whether positive or negative, doesn't exist. Find out which MyMathLab does. You'll be able to find that out by doing an example. If you get it wrong, then try the other way. So if you find the left and the right limit is both positive infinity and you try and type in infinity and it says you're wrong, go back and try and do does not exist and it should mark it right. And the reason I'm telling y'all is because I use 3 or 4 different, I wonder if y'all heard that. My dog hacking. Distractions. Because different teachers, different textbooks have different ideas of whether you should say D and E or infinity or negative infinity if they match. I can't definitively tell you which one it is all the time because I use 4 different math programs and I can't remember which is which. I'm still kind of used to WebAssign because that was what we were using the last time I taught this class. And like I said, it'll be a really quick check. So make sure you figure out which one MyMathLab does in the homework. That way, when you get to the testing, you'll know which it is. And I will check out MyMathLab and remind myself which one it is. That way, nobody screws it up for a test and loses points over something they shouldn't have lost it. Me personally, I prefer saying that the limit's infinity or the limit's negative infinity because that is a unique answer. It's an A or a B. But some people just like to say, well, neither of those numbers exist, so let's say it doesn't exist. But the problem is there's still times where it going to the top or going to the bottom matters. So saying that, giving it distinction can be helpful. So again, kind of a special set of notes. All right, and last example for the day, I think. I think we'll call it here if we have a few extra minutes. I don't want to start a new section with 5 or 10 minutes. And let's actually get to the continuity stuff. A, find the limit as x approaches 10 for f of x, and I'll put that down in a minute. And then for B, is it continuous at x equals 10? And our function is going to be piecewise defined. And it's going to be x plus 7 and 2x minus 3. The top one will be for x is bigger than or equal to 10. Bottom one will be for x is less than 10. So because the top one is only true for the right side, the bottom is only true for the left side, what you'll do is for the limit is plug 10 into the top to get the right-hand side limit. That's what RHS means. And then you'll plug it into the bottom to get the left-hand side limit. So for the top, f of 10 is 10 plus 7, which is 17. So the limit, now that's for numbers bigger than or equal to 10, so that's coming from the right. It says x goes to 10 from the right of our function is equal to 17. For the bottom, f of 10, and I'm going to put a little asterisk next to that because you're technically not supposed to plug the 10 in here, but we talk about this in pre-calc 1, how you can do it just to see things like continuity, whether you have open and closed circles or it just keeps moving. So that would be 2 times 10 minus 3, which is 20 minus 3, which is also 17. So the limit as x approaches 10 from the left is also 17. So the limit exists. So the limit as x approaches 10 of this function is 17. So that's the answer to A. For part B, we ask, is it continuous? Things are only continuous if the limit matches the actual function value. So we have to find f of 10, which we already did. We must use the top because that was the one that had the or equal bit right there. And we already showed the math. It was 10 plus 7, which is 17, which is the limit. So it's continuous. I'm just going to abbreviate at x equals 10. It's actually continuous everywhere, but we were only interested in the 10. Okay, so let's say that the left side and the right side limits didn't match. There wouldn't be a limit, which automatically says it's not continuous. What I'd like you to do on your own, and I'm not going to do this for another one, try to do this again with this function. The same top one of x plus 7 for x is bigger than or equal to 10. And then 2x plus 3 instead of minus 3 for x is less than 10. You should find that there is no limit, which immediately says it's not continuous at that number. But I want you to show your own work for that. I'm not going to collect or anything. It would just be a good exercise for you to do. All right, so that's it for that section. Just give me a minute while we set up. All right, so like I said, that was it for 1.1 and 1.2, and now we're going to begin our journey into 1.3. Pages. So 1.3, the average rate of change. The average rate of change. So a rate of change is something that we've already talked about. Rate or ratio means fraction. Change, unless you're getting into like percentages, this is generally a difference. So the word rate of change is a fraction of differences. Remember slope? Slope is a rate of change because this is a fraction of differences. And that formula, as a reminder, is m equals y2 minus y1 over x2 minus x1. You are calculus students. You never, ever, 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 ever get to forget that formula. If you forgot it, learn it now, learn it yesterday, learn it a week ago. You never get to forget it. Things with slope, things with equations of lines, you never get to forget it. It's not allowed. It will be a problem for now and the rest of your lives if you forget it. I can guarantee that. So, excuse me. Slope, that letter m, which I wrote a little sloppy, but that's an m on the left, is a y2 minus y1 over x2 minus x1. Let me do this. And why is that blue all of a sudden? I don't know. Now you don't want to give me color options? Technology, am I right? Okay. Just keeping this in the first quadrant to make things as easy as possible. Let's say we have our first point here, and we have our second point here. So P1, P2. Now each of these points has coordinates. P1 is x1 comma y1, and then P2 is x2 comma, that looks like a semicolon. Come on, thank you, comma y2. So if this is point 1, then on the x-axis that has to be x1, and if this is point 2 on the x-axis, this has to be x2. On the y-axis, very similarly, this height would have to be y1, and this height would have to be y2, because that's how coordinate pairs work. They tell you how far left, right, up, or down you go. The first one being the left or right, the second one being the up or down. And then we could connect those points with a line. And the steepness of that this distance right there, that's the horizontal distance known as the run. And then this vertical distance is known as the rise. And the run and the rise are literally those differences of x2 minus x1, that looks like a y, and then this one's y2 minus y1. So the slope is just the ratio of those two lengths. So that's the slope of a line. But we want to get into, start talking about the slopes of curves. And to introduce that idea, because lines have a constant slope, it means it never changes. So the steepness at this point is the same as the steepness at this point is the same as the steepness at this point. The slopes at any point, the slope at any point on a line is always the same. If the slope here is 2, the slope here is 2, the slope here is 2, the slope here is 2. So that's algebra. We're calculus students. So now we're going to get into curves. Once again, I don't know why it keeps changing me to blue, but it is what it is. So curves bend. They could do something like this. And it probably goes on to the left as well, but it doesn't have to if it's a real life function. So let's say, once again, why am I in blue? It says it's blue, but it's black. I'm extremely confused. It's never done that to me. So let's take, I don't know, this point right here. Let's call this P1. And let's call this P2. Now what I'm going to make is a secant line out of those. So I'm going to make a little secant line. And I do actually want the secant line to be blue. And that's not going to be a good steepness. So this is what we call a secant line. A secant line goes through 2 points on a curve. You have a point here and a point here, you connect them. Or I could do it here and connect them. That would be a secant line using that and that. Or I could have a secant line here and I could connect those, but I only want to see one at a time. So every curve has literally millions and trillions of possible secant lines that you can make out of it. It's about why you want to do a particular secant line. Now, slope is a measure of steepness. Now, once again, this line has a constant steepness. It's always the same steepness or grade or slope or rate of change, no matter what you want to call that. They are all the same thing. This curve is bending. It's going up and then it's coming down and then it kind of flattens out and then it goes back up and it could be doing a bunch of different things after that. So curves bend, which means the slope here is different than the slope here, is different than the slope here, is different than the slope here. The slope is different at every single point. Now, there may be some points where like the slope here might be the same as the slope here. There might be some coincidences, but the slopes can all be different numbers. They don't have to match, they don't have to be the same. So to start off calculus, what we do is we say, all right, well, let's find the slope between 2 points on the curve, and we'll call that a secant line, and the slope of that line the slope of a secant line is the average slope of all points between P1 and P2. Now, that might seem like a lot to grasp your head around. Maybe just take it with a leap of faith. But in other words, so the slope at this singular point, if you want to talk about the slope of a singular point on a line, you have to use what's called a tangent line. Tangent means touch and go. So like here at P2, let me do it in red. P2, because the curve is kind of going this direction, the secant line is basically just you drawing a line parallel to it at that singular point. So this is a tangent line at P2. This would be a tangent line at P1. And you can see those lines have a drastically different slope. P1 has a positive slope, P2 has a negative slope. That's the biggest difference between them. Now, what I'm saying is if you measured the slope at the infinitely many points between P1 and P2, if you then added up all those slopes and divided by however many you actually used, that value would be the same as the slope you calculate from P1 to P2. The slope of a secant line is the average slopes of all points between them. So that's a good starting point for getting into calculus, which is trying to find the slopes at these singular points, to find the slopes of these tangent lines instead of using secant lines. So the slope of a secant line, this is what we call our average rate of change. So the average rate of change from P1 to P2 with coordinates x1 comma y1, it's going to take me too long to use subnotation, and x2 comma y2, but you all should know that it has the little subnotation like up here. It should look just like those. So the average rate of change from P1 to P2 is literally the definition of slope. It's y2 minus y1 over x2 minus x1. But it's better to use function notation. So function notation, instead of y1 and y2, you have f of x1 and f of x2. So y1 is f of x1, and y2 is f of x2. So our average rate of change, and this is the formula I stick with, AROC, average rate of change from point 1 to point 2, is f of x2 minus f of x1 over x2 minus x1. This is literally the formula for slope. This was something that was done in pre-calc 1 as well. This is a formula you have to have memorized. So this calculates the average slope from one point to a second point. That's what this will do for us. It doesn't tell us the slope at the first point. It doesn't tell us the slope at the second point. It does actually tell us the slope of at least one point in between. There's a theorem for that we don't need to worry about too much in here, but it's kind of cool that it does say at least one point has that slope. But again, this is just the slope of a secant line. So let's try out an example. And that's in blue. Give me black. Yeah, so usually that color shows what I have picked. It's probably because Word crashed earlier. So we're going to, for this example, find the average rate of change of the function f of x equals x squared from x equals 3 to x equals 6. And this is going to be example 1a. For example 1b, we're going to use the same function, but we're going to do it from different x values. So we're going to find the average rate of change for the function x squared, our very, very basic introductory parabola, from x values of 3 to 6. Now you need completed points to do this. All I gave you was the x values, but you can find y values by plugging them in. So the first thing you have to do is plug in to find the y values. And I'm putting that in quotes because we're going to call them function values, f of x2 and f of x1. So f of 3, that would be 3 squared, which is 9. That is our y2 or f of x, I'm sorry, y1 or f of x1. Because 3, we're going to call that the x1, 6, we'll call that the x2. So when we plug in 3, we get a 9, that's the function value, that's the output. Similarly, if we do f of 6, we'll get 6 squared, which is 36. That is our second output. That's what we call f of x2. That's f of 6. x1 is the 3, x2 is the 6. You can see the numbers you plug in that associate with them. That's one of the advantages of function notation we talked about last time. So now the numbers that we need are the 3, the 6, the 9, and the 36. All we're doing is calculating a slope using that. That is literally what an average rate of change is. So why does it keep going back to blue? Average rate of change. That's f of 6 minus f of 3 divided by 6 minus 3. y2 minus y1 over x2 minus x1 literally means the same thing. But the f of 6 was the 36. The f of 3 was the 9. So we got 36 minus 9 in the top. In the bottom, that's just the 6 minus the 3. 36 minus 9 being 27. 6 minus 3 is 3. And 27 divided by 3 is 9. So that is the average slope from x equals 3 to 6. If you do any different x values, that is likely to be a different average slope. That is averaging the infinitely many individual slopes at singular points that we don't even know how to calculate at this point. It's unfathomable at this point to us, but not for long, thankfully. But if you were to calculate that infinitely many slopes and then average them out, it would average out to 9. Let's try another one. For B, for B, let's go from x equals 0 to 3. Now, you don't have to call the 0x1 and the 3x2. You can call the 3x1 and the 0x2. Just make sure that your function values are labeled accordingly as well. If you call the 3 the x1, then when you plug that in and get 9, then the 9 is the f of x1 this time. So again, it might be a good idea to label them. I'm calling the x1, that's the x2. So f of 0, that's the f of x1. That's 0 squared, which is coincidentally 0. That's our f of x1. F of 3 we've literally already done. That's 3 squared, which is 9. So that's our f of x2. See, last time I called that f of x1, this time it's f of x2, because last time the 3 was the first point, this time it's the second point. So our average rate of change, that's f of 3 minus f of 0 over 3 minus 0. So again, the numbers we're plugging in are the 9, the 0, 3, and the 0. So the f of 3 was the 9. Whatever, I'm not changing the color again. The f of 0 was 0. Then the bottom was just 3 minus 0. We already have those numbers. 9 minus 0 is 9, 3 minus 0 is 3, and 9 divided by 3 is 3. It has a much smaller slope. Now, let's, for fun, actually after we do this, for fun, let's do one more C. Maybe a little less work on C. But let's go from x equals -3 to x equals +3. So f of -3 is -3 in parentheses squared, which is +9, not -9. F of +3 we already know is 3 squared, which is 9. So our average rate of change, the f of 3 minus f of -3 over 3 minus -3, that's 9 minus 9 over 3 plus 3, which is 0 over 6, which is 0. Huh. So the average slope between those two values is 0. You might think that that doesn't make sense, but we haven't visualized it yet, so maybe that would help. So let's graph this. All right, so we're going to take our 10-minute break right about now. I don't actually have the time. I didn't mean to do that. So it's 7:47, so we'll come back at 7:57 and we'll pick up with a graph showing you the curve and then some tangent lines and just give you a better idea of what everything looks like. All right, let's continue by, like I said, making that graph and just getting a nice visual comparison for the tangent lines of those two different points on that parabola. I'm just going to do it by hand really, really quickly. All these points are in the top portion of the graph, so I'm not going to do too much on the negative portion. We have the point 3, 9. We have the point 0, 0. So here's 3, and let's have a height of 9 be about here. You can see I'm stretching the x-axis a little more than the y-axis. And then we had a point at 6 about here, which had a height of 36, which is probably way up here. And then our curve would look something like this. Pretty standard parabola. Ignore my mediocre artistic ability with this tablet. And then the left side looks very similar. In fact, we did the calculation for the -3. It had a height of 9. If you did the calculation at -6, it would also have a height of 36. So there's our line. So in blue, I'm going to do the first one. We went from 3 to 6, correct? Yes, from 3 to 6. So in blue, this will be the first secant line connecting. That doesn't look great. This point and this point. So this would be the secant line for A, and that slope is 9. Now in red, I'll do B, which was going from 0 to 3. So if you connect these 2 points, you can see that we still have a positive slope. This is B's secant line, but it is definitely smaller. It's not as steep. We came over the slope of 3. So we can see that the secant line going from 3 to 6 is a larger number. We can see visually it's steeper. Larger number, steeper. Smaller number, less steep. Now let's do from -3 to 3, and let's do that with a, how about dark green? So again, here is that point, here is that point. So if we connect them, it's a horizontal line. And guess what? Horizontal lines have a slope of 0. You were supposed to know that fact inside and out. So again, those lines, those secant lines, are a great visual representation of the average slope, because when you see that line, you can see, hey, that line C, it's flat, so it should have an average slope of 0. Even though the infinitely many points from -3 to 3, this is a negative slope. This is probably like a negative, -6. It would be exactly -6 at -3. Don't ask why I know that. We'll find out later. And then it would be something like a -2.5, and then a -2, then a -1, and then a 0. The slope here is 0. This tangent line would be completely horizontal, which you can barely see that, but it would be 0. Again, I said tangent, not secant there. It's the only one I'm going to describe. And then we end up like a slope of +1, +2, +6, and then over here at 6, that would be 12. So if you averaged all those slopes from 12 to 6 between those, you end up getting 9. In fact, the average of 12 and 6 is 9, but that's just a coincidence. And that's because quadratics have cool features like that. So this is something we did in pre-calculus. This is nothing new. This is nothing new. So what do we do in calculus? What we want to do in calculus is find a way to talk about the slopes at a single point. Instead of using 2 points, we want to talk about the slope at 1 point. So in calculus, what we do is we want to merge the 2 points from an average rate of change formula into 1 point. We do this by saying the second x value is an arbitrary constant, which we label as h, added to the first value. So in other words, when I talk about the x value 6 in comparison to the x value 3, 6 is 3 plus 3. So I could say that h is 3. It's a coincidence. If I wanted to talk about 7 in comparison to 3, then the h would be 4. If I wanted to talk about the value of 3.5, that would be an h value of 0.5. It's just the difference between the two numbers. the 2 points. Let me delete my second the. So in calculus, we want to merge the 2 points. We want to take them and squish them together. We want to take the second one and just kind of slowly make it closer and closer and closer in theory. The idea of taking a number and making it closer and closer and closer to something. That sounds familiar if you watched the last class's lectures, which I know everyone has. This idea is the same as a limit. We want to get smaller and smaller and smaller to merge these points. So that idea, like where we had a function and we plugged in 0.9, then 0.99, then 0.999 to take a limit, the idea here is to make the h something like a 1, then a 0.1, then a 0.01, then a 0.001. And then you just see what the number is getting closer and closer and closer to. Okay. So instead of using x2, we call x2 x1 plus h. And again, those are supposed to be little 2's and little 1's. This makes the average rate of change formula change into this thing. Color. So our average rate of change becomes f of x1 plus h, because that's f of x2, minus f of x1, over, now x2 is x1 plus h, and then minus the x1. I'm going to scroll up real quick to show you the comparison here. The two things that I'm highlighting, these used to say x2. See right here, f of x2 and then x2. But we just said we're going to make x2 the first one plus that arbitrary h. So h is just a small number. It doesn't have to be small. It can be 1,000 or 1,000,000, but because we're trying to merge the points, the idea is we want it to be small. But arbitrary because it could be 1, 0.1, 0.01, 0.05. It doesn't have to be 0.01 or 0.0001 or anything like that. But check this out. x1 in the bottom minus x1 in the bottom, those two things are going to cancel each other out. And what this thing turns into, this is getting frustrating, is f of x1 plus h minus f of x1. The top does not change, but the bottom does. The bottom is just an h. This right here is known as, and again, this was seen in calculus, the difference quotient. But we don't have to use the little sub 1's. So the final way I'll write this is f of x plus h, then minus f of x, all divided by h. I'm going to box this one up because this is the best format. Why? Because when you use x, you're implying that you can plug in any number that you want. So by doing that, it gives me the original version, but also it means I don't have to plug in an x. I can actually get formulas for this thing based on any x value, not just a specific one. So what I'd like to do is use this and go back to the x squared function and create an example with these h values. Now, I will admit, this is not a typical sequence that I'm going to have us doing in this class. This is going to be I'll do it once, you'll see some in the homework, and then I'm probably never going to do it again because it is extremely time consuming. It's more of a numerical methods approach, and it's just to get us an idea of how things work. Okay, so example, what do we have to? 2? Yes, example 2. So for the function f of x equals x squared, once again, find the average rate of change for an x value of x equals, most of those were centered around 3, so let's stay close to the 3. And then with h's, for a, we'll do 1, which is honestly too big. For b, we'll do 0.1, and for c, we'll do 0.01. So we are actually going to be plugging in numbers for h. This is something you'll never see me do again in this class. What values are we plugging in? 1, 0.1, and 0.01 as separate problems. And I'm going to need some space, so let me scroll out. Let's put a right here. So again, our x value is 3, and our h is equal to 1. So our average rate of change is f of 3 plus 1 minus f of 3 all over, and it's just h. Remember, the bottom is not x2 minus x1 because we did that little quick substitution and it changed the bottom's format. And this is really, really popular. You're going to see this. You need to memorize this now and for the rest of the semester because it's going to be a common theme in chapter 2. So the bottom is just the h, which we said is 1. Well, 3 plus 1 is 4, so that's f of 4 minus f of 3 over 1. I'm not going to show the plugging in. 4 squared is 16. 3 squared is 9. We've already done that. So that's 16 minus 9 over 1. 16 minus 9 is 7. So that's 7 over 1, which is 7. What we have just done is found the average rate of change between x equals 3 and 4. That is seen literally right here because when you plug in the 3 plus 1, the x plus the h, it's 4. This is not a new type of problem. If you go back and do the average rate of change from 3 to 4 in the previous example, you would be doing 16 minus 9 over 4 minus 3, which is 7 over 1, which is still 7. Okay, so that's the slope of the tangent. Sorry, I said it right the first time. That's the slope of the secant line going from 3 to 4. Now let's start at 3. But let's have it a lot closer. We're going to have the h be 0.1, which means we're going from 3 to 3.1. So our average rate of change, is f of 3 plus 0.1 minus f of 3 all over just the h, which is 0.1. So that's f of 3.1 minus f of 3 divided by 0.1. We'll pull out a calculator to make this easy. 3.1 squared is 9.61. So that's 9.61 minus 9 divided by 0.1. I need to continue this down here. 9.61 minus 9 is 0.61, so that's 0.61 divided by 0.1. Now, you should not need a calculator to do this. You are calculus students. You should know how to do decimal divisions. This is the same thing as if you move each decimal right once, 6.1 divided by 1, which is 6.1. So that says the slope of a secant line from 3 to 3.1, very close together, is 6.1. C. Let's go from 3. So again, this was going from 3 to 3.1. Now let's go from 3 to 3.01. So this is 3, adding 0.01 to that would be 3.01. So these 2 points are really close together. In terms of graphing, you're going to have a hard time doing that by hand. Give me about 15 seconds. I need to drink some water. All right. So our average rate of change would be f of 3 plus that very small 0.01 minus f of 3 all over 0.01, which is f of 3.01 minus f of 3 divided by 0.01. So let's square 3.01. 3.01 times 3.01. And you get 9.0601. 9.0601. 90601. Minus 3 squared is 9 still. Then divide that by 0.01. Subtracting the top gives you 0.0601 divided by 0.01. Dang it. I was talking, sorry about that. When I had that last cough, I forgot to take my mute button off. All right, so was the last thing I said this 6.01? Was the last thing you heard me talking about when we boxed up the 6.01? Okay, cool. So I will now say out loud what I was saying again. I apologize for that. Surprisingly, that's the first time that has happened in a whole semester. Well, I guess half a semester since we started this in March. Okay, so thank you for catching me on that. So what I was saying was, when we had an h value of 1, the slope between going from 3 to 4 was 7. Then we went from 3 to 3.1, and it was 6.1. Then from 3 to 3.01, it was 6.01. So as we make this h smaller and smaller, we're getting closer and closer to a value of 6. So we say, what does the average rate of change seem to be approaching if we keep making this h smaller, like a 0.00001? It would probably be like 6.00001. It seems to be going towards 6. So what that is suggesting is that if we want to take those 2 points, x1 and x2, and merge them together, let's just take the limit as this h goes to 0. We want to squish them together, which means the h goes to nothing. The x1 becomes the x2. So we say, maybe we should take the limit of this difference quotient as h goes to 0. Now, what this gives us is our instantaneous rate of change that I did not spell correctly. It's instant with an A. Capital A. So this will give us what we'll call an instantaneous rate of change at a single point. This right here is the first step of calculus. By throwing a limit on the difference quotient, we are now doing calculus. The difference quotient is something that you did in pre-calculus. The limit is something that we said, all right, this is the first step of calculus. Taking limits is our first step. But this is really the first step because the study of calculus is all about change. And this gives us our first idea of real change at a singular point instead of multiple points. We can come up with the slope at 6. So for example 2, example 3, I used to call it example 2 in my old notes. It's now example 3. Let's find the instantaneous rate of change of the function f of x equals x squared at x equals 3. So what we want to do is take the limit as h goes to 0 of that difference quotient formula. So of the difference quotient. This gives us an instantaneous rate of change. So that's the limit as h goes to 0 for f of, now we said our difference quotient was this formula, f of x plus the h minus f of x over h, where our x is going to be 3 and the h we're going to leave as h. All over h. And I wrote an x here, I meant to write a 3 there. Let me just undo that. Bad habit. I will also point out this is another case of we usually don't do things this way. We're usually not going to plug the number into the definition, which is this. We are generally not going to plug the number in here. In the next section, you'll see what we generally do. This is kind of a one-time only thing. But let's just see what happens at 3 specifically. So we don't plug in the h because we're going to make it go to 0. So we don't want to go through that 0.1, 0.01, 0.001 nonsense. But we do want to know what happens specifically at x equals 3, so we're plugging that in. So f of 3 plus h, this would be the limit as h goes to 0 of 3 plus h squared minus, when we plug in 3 to the function, that's 9. We already know that. F of 3 is 9. That's because we're just squaring the input. And then over h. Now, if you try and plug the 0 in right now, it's going to make the bottom 0. If you plug it in here, 3 plus 0 is 3, 3 squared is 9, 9 minus 9 is 0. You get 0 over 0, which is indeterminate. You have to wait to plug it in. How do you know how long to wait? Generally, you'll see something massive cancel. Generally, the h in the bottom needs to go away. So this is the limit. As h approaches 0, let's simplify the top. The 3 plus h, we can FOIL that out. So that's 3 plus h times 3 plus h, then minus the 9 all over the h, equals, and yes, you have to keep writing the limit as h goes to 0 until you plug it in. We're going to FOIL the 3 plus h. 3 times 3 is 9. 3 times h, that's a plus 3h. The inner is the same thing, h times 3, that's another plus 3h. And then the h times h is a plus h squared. We have the minus 9 at the end. I'm just going to put a little really thin parentheses around this. You don't need it. I'm just trying to emphasize that that was this. The minus 9 at the end is just still the minus 9 at the end. And the bottom is still an h. Now again, those parentheses are not really there. That was just for visual flair. Look what happens. The 9 and the minus 9 cancel. This 9 and this minus 9 cancel. Gone. Gone. The 3h and the 3h will stack to a 6h. So this is now the limit as h goes to 0 of 6h plus h squared all over h. And if you plug in the 0 now, it's still not going to work. The top and bottom are both 0. But what we can do now is, in the top, there's a GCF. This is a very common issue. So let's factor it out. So that's the limit as h goes to 0. Take an h away from the 6 and the h squared. What are you left with? Taking it from the 6h, you're left with 6 plus h squared had 2 of them. Now it's only got 1 of them when you take 1 away. And the bottom, you've got an h. Well, with an h in the top factored and an h in the bottom factored, they cancel. So this is now the limit as h goes to 0 of just 6 plus h. And if you plug in 0 into this, you won't get that indeterminate form. In fact, there's no more denominator. So now we can plug in. So this becomes 6 plus 0. Oops, it didn't change the color that time. Which 6 plus 0 is 6. Now before, we thought that it was approaching 6. It went with a mediocrely large h, it was 7, then 6.1, 6.01, the next would have been 6.001. So this confirms that. If you somehow manage to plug in 0.000000000000000 with 10 billion quintillion infinitely many zeros, you'd get 6. So that says the slope at x equals 3 is 6. At the singular point, you no longer need 2 points. It's not an average slope. It is the slope at that singular point. Now, the slope at that point would be different than at 0. It would be different at 12. It would be different at -3. It would be different at +6. And you think, wow, I'd have to go back and count and do this math every single time just to do it at a different number. And in fact, you don't. Which is why I said earlier, this is not the way to do things generally. There is a much simpler and a much quicker way to do this. And the way that is instead of plugging the number in, you leave these as x's, you'll get a formula in the end to then plug the 3 in, or the 6 in, or the -12 in, or whatever number you want to. And then you can find slopes at different points as quick as snapping your finger 10 times, or 9 times, or however many times I just did it. So again, this works, but it's a pain in the butt if you have to do this for multiple x values. So not my suggestion, but it leads us into how we're really going to approach things. Okay, so that's about 50 minutes in. Pretty good timing. That is 1.3. So 1.4. Differentiation using limits of difference quotients. Differentiation is exactly what we just did, arguably. Differentiation kind of sounds like difference quotient, differentiation, difference, they're similar. So differentiation relates to the difference quotient. So that's why we say doing differentiation using limits of difference quotients. There's another word for differentiation. Derive Why did I spell with an I? That was silly. Differentiation is the process of finding a, and I want to have this all caps. Excuse me, is the process of finding a derivative, which is the instantaneous rate of change at any x value, not a specific x value, at any x value. So there's a lot of words that all mean the same thing. Instantaneous rate of change, derivative, differentiation, limits of different quotients, all these mean the same thing. Tomato, tomato. Is it synonyms? Pseudonyms? I was thinking homonyms at first, but that's not right. That's when they sound similar. Pseudonyms. So the derivative of a function, f of x, is the instantaneous rate of change at any x, and has the notation f prime of x. Kind of looks like a exponent that's a colon. I usually don't have it so bendy. Usually just looks like that. Kind of looks like an exponent of 1 on the f. That is what we call prime notation. That is called prime notation. So that is read as f prime, or the derivative of f of x. F prime means the derivative of f of x. All of these things relate to slope. At a singular point. Instantaneous rate of change is a slope at a singular point, as we already said. I'm just saying the same things over and over to make sure that we really get the idea. So what does this look like? F prime of x, the derivative at a specific x value, is equal to the limit as h goes to 0 of the difference quotient, which was f of x plus h minus f of x, all divided by h. This is the limit definition of the derivative. Derivatives are slope. Instantaneous rate of change is slope. F prime of x is slope. This all relates to how a function is changing. Calculus is the study of change. Unless you're a dentist and it's the study of the gunk between your teeth. But for us, calculus is the study of change. So again, we just do the difference quotient. We take the limit as h goes to 0, and bam, we will get a formula, and that formula will describe the slope at any point. So we don't have to do the difference quotient for an x value of 3, then at an x value of 6, then an x value of 9. You don't have to do all that crazy math we did last time. You just do it once, and then at the end, you get a formula to plug your numbers in that will be much, 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 much simpler. Like me, I knew this answer was 6 because of that simple formula. It makes things a lot easier. Now, we will go back and do the x squared problem again, but let's do a simpler one to start this out. Example 1. And we are going to, let's do it here. Find the derivative derivative of the given function. Find the derivative of the given function. For a, we're going to have f of x be 2x minus 6. So this is our function. Now this function is a line. Lines have constant slope. And in fact, if you remember your algebra, which you better, we'll remind us of those equations of lines once again in a few examples, but the number in front of the x, if it's solved for y, which f of x acts like y, this is the slope. So you should all know instantly that the slope of this line is 2. And because it's a line, the slope is 2 everywhere. But now let's use calculus to prove that. So we are doing calculus. So f prime of x. This will be the limit as h goes to 0 of f of x plus h minus f of x all over h. So we're plugging the x plus h into the x. So x plus h is what's going to go where you originally saw an x. If you need to do that to the side, you certainly can, and that's the way I do it in pre-calculus, but I show everything in one instance in calculus, but you are always more than welcome to do some stuff to the side. So this will be, I need my, and I'll do colors, so f of, not yet. I almost want to close this and open another one and see if it's going to be silly still. So this is 2 times the x plus h. It also makes me just want to do everything in blue. Minus 6. This right here, all I have right now, just this, that's f of x plus h. So instead of 2 times x, it's 2 times x plus h. And then there's a minus 6. So all this that I have circled, and the circle is going to go in a second, that's the f of x plus h. So then we have our minus. And this is supposed to be the f of x. F of x. So minus f of x. Now f of x is 2x minus 6. I'm going to write this incorrectly at first. This is wrong, this is wrong, this is wrong, this is wrong. And then you go over. So just temporarily highlighting. This highlighting was the f of x plus h. This highlighting is the f of x. Why is this wrong? Why in the world is this wrong? Because I have the minus and then I wrote the f of x. Well, this minus is supposed to go to the whole function. This is a very, 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 very common issue. Almost every time you need to wrap that f of x in parentheses. This is very common. If your function has more than one term, if you want to subtract it, you got to wrap it in parentheses. You were supposed to have mastered that in arithmetic and algebra classes. And then the bottom was just supposed to be our regular old h. Remember, we're not plugging anything in for h. We're leaving h alone until the very, very end, and we make it a 0. If you try and plug it in now, I guarantee you, you'll get 0 over 0, which is indeterminate. All right, so this is equal to, let's keep going, distribute the 2. So that's the limit as h approaches 0, 2x plus 2h minus 6, distribute the negative, so that's a minus 2x plus 6, watch your signs, all divided by h. Well, there's some stuff that can cancel. This is very, very, very common. 2x minus 2x, gone. Negative 6 plus 6, gone. With polynomial functions, you should get a decent amount of cancellation. In fact, any term that doesn't have an h ends up canceling, spoiler alerts, for polynomials, not necessarily radicals or rationals. Those are different issues. Okay, so equals. What are we left with in the top? Just the 2h. So that's the limit as h goes to 0 of 2h divided by h. Well, look at that. You have h's on top of each other, so they cancel. Gone, gone. So that's the limit as h goes to 0 of 2. Now, if you plug in 0 here, you're going to get a perfectly fine form. You cannot have h's in the denominator. Otherwise, you're going to end up indeterminate. I can guarantee that. You are looking for this cancellation. Once you see this cancellation, that's when you know you can plug it in for polynomials. And usually for others as well, but there's exceptions to every rule. So where do I plug the 0 in? I don't see an h. Well, if this said 2x and I asked you to plug in x equals 5, you wouldn't. You would just leave it as 2. If there's no variable, you don't plug anything in. So the answer is just 2. You can't plug it in this time. This is kind of a simple case. Usually you can plug it in. And you'll see that in the next one. Don't worry. So at the very beginning of this problem, I told you I know slopes 2. I know it for several reasons. First reason I know is because this is an equation of a line, and the number in front of the x is supposed to be the slope as long as it's solved for f of x or y. So look, that matches with what we got. I also know some slightly more advanced calculus, and I can just look at that and know the answer in other ways, but we're going to teach you that, don't worry. There are quicker ways to find this answer for more complex polynomials, thankfully. But we got to do it the hard way before we do it the easy way. B, f of x equals x squared. Now, I'm not saying at x equals 3 this time. I'm just saying in general. So when we're done with this, we'll get a formula. And if I wanted to know specifically what the slope is at 3, I could then plug 3 into the formula. And then I could find out what happens at 0 and 6 and negative 12 and whatever x value I want without having to do this painful algebra every time. You'll only have to do it once. So we're supposed to find the derivative of this, which means we're finding this guy, f prime of x, which the definition of the derivative is this limit thing, the limit as h goes to 0, and it's f of x plus h minus f of x all over h. Again, we are using this formula right here. I'm even going to highlight it. Don't you dare ever forget this formula. You won't be using it constantly throughout the semester, but it will come back and bite you every now and then. All right. So the limit as h goes to 0 of f of x plus h. So the function is x squared, so this should be x plus h squared. Then minus the f of x, which is just the x squared. That's always given to us. The minus part's always given to us. It's the f of x plus h that you'll have to do some jazz with. And then all divided by h. Again, this was originally just a sloped formula that we have made more complicated because we want our 2 points to become 1. All right, well, this parentheses squared, that's the limit as h goes to 0 of x plus h times x plus h, then minus the x squared, leaving that part alone, all over the h. So this is the limit as h goes to 0. We're going to FOIL out that parentheses, pair of parentheses, x plus h times x plus h, and you're going to see this multiple times in this class. You should have seen it in pre-calc multiple times as well. That's x times x is x squared, plus the outer x times h is xh, or hx, the order doesn't matter. The inner is the h times x, so again, it can be xh or hx. The x or the h can be first, it doesn't matter, but be consistent. I went xh, so I'm going to go xh again. Again, the outer and the inner match. This is pretty common to see for binomial squares. Then the last is the h times the h, which is h squared. So again, these 4 terms right here, we're just foiling out the parentheses. Then we have the minus x squared that was already there. Then we have the all over h. Do not be lazy and skip writing the limit. Do not be lazy and skip writing the over h. When you're lazy, you end up forgetting them later and missing them and getting things wrong. I can guarantee it. Been there, done that, bought the t-shirt. These get really ugly for a hot second, but the good thing is lots of things will cancel. The x squared and the minus x squared are gone. The xh and the xh add to 2xh, adding the same thing. Apple plus apple is 2 apples. So xh plus xh is 2xh. So this is the limit as h goes to 0 of 2xh plus h squared, all divided by h. Again, after combining like terms and canceling. Now, just like in this previous problem, when we had a GCF in the top, h, we need to factor that out and cancel it to get rid of the h in the bottom. Same thing happens here. There's an h and an h, so we can factor it out and cancel. So here's the GCF again of h. So this is the limit. As h approaches 0, take the h out of the top terms. What are you left with? From the first one, the 2 and the x are still there, plus from the second term, it had 2, so there's 1 left over. Then this is all over h. And we have now hit the point we've been waiting for. There's an h as a factor in the top and h as a factor at the bottom. They cancel. So we get the limit as h goes to 0 of just 2x plus h. This is your signal. This is your flare. When the h's are gone out of the bottom in general, that's when you can go and plug the 0 in. If you plugged it in at any point before now, you'd get 0 divided by 0. Don't believe me? Try it even at the last one. This would be 0 plus this would be 0 divided by this would be 0, which is 0 divided by 0. Indeterminate. Nobody knows what it is. But now we can plug it in. So that's 2x plus plugging the 0 in. Just gives us 2x. So the better way to write this, instead of just writing the 2x, use the notation. The derivative of the function, in other words, the function that guides its slope, that dictates its slope no matter what x value, is 2 times x. That is the formula for the slope at any point of the function. That is amazing. I don't think a lot of people really understand how amazing that is. We are able to calculate the slope at a singular point, not 2, at a singular point without having to take the h going from 1 to 0.1 to 0.01 to 0.001 without that big process, just some, not the simplest algebra in the world, but stuff you should know. And we get a relatively simple formula to plug in an x value. So if you want to know what the slope is at x equals 3, plug in 3 here. Guess what 2 times 3 is? It's 6. So I'm going to make a little memo of that. At x equals 3, f prime of 3, so that's saying the slope at 3 is 2 times 3, which is 6. And that agrees with what we got before when we did the limiting process with the h's getting closer and closer to 0. We deduced that we were getting near 6. Then by doing very similar algebra, but by plugging the 3 in first, we were able to see that the slope is 6. But if you do this problem the original way, and I now ask you, all right, well, what's the slope at 6? What's the slope at 7? What's the slope at 9? You'd have to do all of this work again. Whereas the way we just did it, all you do is plug in 6 or 7 or 9 here. So the slope at 7 is 2 times 7, which is 14. The slope at 9 would be 2 times 9, which is 18. The slope at 0, 2 times 0 is 0. I can fire these off in like a half a second each. The slope at 1, 2 times 1 is 2. The slope at 17, 2 times 17 is 34. These formulas are amazing because very often in the real world, we want to study change. These things called marginals in economics, if you will, not margarine, marginals. When we talk about like the speed of a car, that's change. It's change in position. When we want to talk about acceleration, that's change of speed. These are all derivatives. These are all fascinating concepts. So derivatives, rates of change at a singular point. What is happening right now? Hey, this virus that's going around, how is it changing? Because we might only want to look at a singular day because yesterday doesn't matter anymore necessarily. I want to make another memo here that when we got to, from the previous example, the limit as h goes to 0 of 2xh, didn't need that there, plus h squared all divided by h. I want to show you an alternate way. The way I've done this 2 times in a row is I took a GCF out of the top and then canceled. Your calculus students, if you know a shortcut here, please feel free to use it. You can cancel a factor while it's written in a non-factored version as long as it's everywhere. So because that h is in this term, and this term, and this term, it's in every single term, top and bottom, you can cancel it. If it's missing from one of them, you can't. So I'm going to just pretend for a hot second. If this h was not here, I could not cancel the h squared and the h. I could not cancel a factor there. I could not do that because the h isn't everywhere. But typically what you'll see is that it is. So I can say, all right, get rid of this h, get rid of this h squared and make it an h to the first because there were 2 and now there's 1. Get rid of this h. And now what we have is the limit as h goes to 0 of 2x plus h. The bottom's gone, so I don't need to write it. This h squared is now an h to the first. And you literally get the same answer. I do not care which way you're doing this when you show your work. I care that you have a method that works for you every single time. So again, also just as kind of extra work, if you wanted to know, all right, well, what's the slope at 0? Well, that's 2 times 0. You're using the 2x, not the original function. That's 0. So the slope at 0 is 0. What's the slope at 10? At x equals 10. What is it currently changing? How is it currently changing? Well, that's 2 times 10, which is 20. This gives us expected values in the near future. So if you know what's happening at 10, you can easily predict what will happen at 11. Whether or not that's accurate, if we're talking real world information, it doesn't have to be accurate, it can be close, but at least we'll have a close estimate. And that's something that, again, these people are doing when they model virus, the population of how many have it, how many have died, how many will get it. There's a lot of calculus involved with that stuff. All right, so let's do another example like this, because again, this is much more common, at least for now. Black. Example 2. Oh no, I'm sorry, this shouldn't be example 2. This is example C, 1C. This is just C. Pardon my mistake. So again, we're going to find the function that will dictate the slope of the function. That's our goal here. We're finding f prime of x for a function. Now let's do the cubic function, the basic cubic. Now we are eventually going to learn a way to do this without the limits. It's a bigger shortcut, and I can tell you the answer right now is 3x squared based on that process. If I had x to the 4th, it would be 4x cubed. If I had x to the 10th, it would be 10x to the 9th. I can do those in less than a second. But before we get to that, we need to practice with the more methodical version of this because it is important. It's important to understand the complicated version before we become masters of the simple version. So we're doing the limit. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. And you should have that formula written down in front of you. So f of x plus h, now we're cubing it. Cubing, not squaring, that's a 3. And we're plugging x plus h in this time. So this is our f of x plus h. Then minus, the f of x is just the x cubed, that's always given. And then all over the h. Or we can't plug in the h equals 0 until that h in the bottom's gone. So this would be the limit as h goes to 0 of x plus h times x plus h times x plus h, then a minus x cubed all over h. Now that's going to get super tedious to show, so let's just do that one to the side. I will do this one to the side. The point of this problem is, this is going to be even more tedious than the last one with the foiling, because we'll have to foil and then we'll have to do something else. If I do an x to the fourth, that's one more layer of complexity. An x to the fifth, that's another layer of complexity. Every exponent higher makes this problem one step longer, in fact. Point being, if I ask you what the derivative of x to the 100th is, you don't want to do that this way. You will hate your life, because you would have a parentheses raised to the 100th power, so you'd be doing x plus h times x plus h times x plus h times x plus h times x plus h, and there would be 100 of those things. And I would cry if I had to do that. So our goal ultimately is to get out of this, but for now, let's make sure we understand how it works by keep stepping it up in terms of complexity. So let's do some side work, and let's do all the side work in green. Okay, so side work. Let's just focus on the x plus h times x plus h times x plus h. Well, the first two we've already done. X plus h times x plus h was right here. It was x squared plus 2xh, the xh and the xh combined to make a 2xh, plus an h squared. So again, x squared plus 2xh plus h squared. That's this. That's the first pair of parentheses. The last one I'll do in red now. So again, I have multiplied out the first two all in green. I just scratched the heck out of myself, ow. But I have not multiplied the last one. There is no special name for this product. Foiling is just a binomial times a binomial. That's how we got this. There's no special name for a trinomial times a binomial. You just have to distribute everything to everything. So distribute the x and the h to the first parentheses. Or you can distribute the x squared, the 2xh, and the h squared to the second parentheses. Distributions work either way. So taking the x, that was weird. Why did those just move? Okay, apparently I can switch that around. So in blue, I'll show these three products. So the x times the x squared is x cubed. That's the first in each parentheses. Then the 2xh times the x, that's a plus 2x squared h. Again, that was the second term or the middle term times the red x. Then the h squared times the x would be a plus x h squared. In, let's go with gray, we'll do the h. So the h times all three of those. So that's plus h times x squared is x squared h. I'm just always writing the x's first for consistency. Then the h times the middle term, h times 2xh is a plus 2x squared h. Then the h times the h squared at the end is a plus h cubed. So let's see. X cubed doesn't have a like term, so that's x cubed. So the first one I'm done with. I'm gonna cross them out as I use them because there's a lot going on. 2x squared h does have a like term. 2x squared h is like x squared h. They have the same variable factors. Now there's an imaginary implied 1 there. So you're adding 2 and 1 to get 3. So that's a plus 3 x squared h. So I did those with squiggles. Then we have an xh squared and a 2x squared. Did I write something wrong somewhere? 2x squared xh squared. I did something wrong, didn't I? The h times the 2xh should have been 2xh squared. This 2 right here I have wrong. I'm going to give you a second. Put that 2 over the h. I think I said it right. I may not have. I just put my exponent in the wrong spot. So I need to erase that. Sorry about that. Terrible looking too. There we go. So in the blue, there should be an x squared h term and an x h squared. In the gray, there's an x squared h and an x h squared. That's correct now. So those two are like terms. So this x h squared and this 2xh squared make a 3x h squared, and then the h cubed is not like anything. So this right here is what's going to be plugged in to the 3 parentheses being multiplied. I'm going to erase that in just a second. But that was the side work. So we can go back to the limit now. So back to the limit. We have the limit, so equals the limit as h goes to 0. So the parentheses times itself, that's the light green ink. X cubed plus 3x squared h plus 3x h squared plus h cubed, then all divided by h. Right? Question mark? No. This is a common mistake that people make. What am I missing? And this is where in class I'd wait for someone to say, you forgot the f of x. The black ink I have right here in the top is just the f of x plus h. So I can't forget the minus f of x, which was the minus x cubed. I can't forget this part right here. I see a lot of people miss that. And then I'll see some people stop here and they're still wrong because they don't have the over h. Okay, a lot of ugly work so far, but all for a cause, because guess what? The x cubes cancel on the top. There are only terms with an h in the top now, which is generally what we want to see. So now we have equals the limit as h goes to 0, 3x squared h plus 3x h squared plus h cubed, all divided by h. If you want, you can just cancel out all the individual h's, or you can take a GCF out. I usually ask who prefers what in class, but I can't ask that right now to every single person and wait 10 minutes for text responses. Since I've done the GCF multiple times, I'll do just the cross out version this time. So there's an h here. There's an h squared here, so that's now an h to the first. There was an h cubed, so that's now an h squared. And this h is gone. I got rid of an h from every single term because every single term had it. If one of the terms didn't have it, I couldn't do it. See, I can't cancel the h's here because there are terms without it. But there are no terms like that here, so I can cancel them, which gives us our limit. Sorry about the color, but I'm not changing it now. Of h, as h goes to 0, of 3x squared plus 3xh plus h squared. Now, we can plug in the 0. So this is the limit. I'm sorry, when you plug in the limit, we no longer write limit, obviously. It's just the 3x squared plus 3x times 0 plus 0 squared. Oops. Which is 3x squared. The middle term is now plus 0. The third term is plus 0, which is 3x squared. So the derivative of our function, in other words, the function that dictates its slope at any x value, is 3x squared. And if you remember, I said that at the very beginning of the problem. I did it in half a second. It's an amazing tool I have at my disposal. There will be problems, at least one, probably two on your first test, and on the final, probably only one on the final, where you have to do this. That shortcut I know that I'm able, oh, it's 3x squared, or if it's x fourth, it's 4x cubed. The fact that I can do that in a quarter of a second, if I give you a problem that says do this by the definition, you have to do this limit stuff. You have to show your work, or you would receive no credit. Now, most derivatives that I ask you about going forward after this section, you get to use this short and simple formulas. And they're not always short and simple, but they're always simpler than the limit version. You have to be able to do things both ways. We will do the limit version much less, but it is still mandatory. You still absolutely have to do that. $12.30, okay. Now, if I wanted to know the slope at, say, 0, 3 times 0 squared is 0. If I want to know the slope at 1, 3 times 1 squared, that's 3 times 1, which is 3. If I want to know the slope at 10, 10 squared is 100, 3 times 100 is 300. Wow, that slope got really large really fast. That's because cubic functions grow really, really fast. They grow faster than quadratic functions. Every larger exponent you have makes the function grow faster and faster. All right. As a reminder, lines. Point slope form is y minus y1 equals m times x minus x1. I gave it to you last class. And slope intercept form, let me just put that a little lower, is y equals mx plus b. If my Algebra 1 students can handle equations of lines, my calculus students better be able to as well. Why do we need to handle equations of lines? Because what we're very often interested in is, let's go back up to some pictures earlier. So these are all secant lines. And we drew up these secant lines. And you could find those equations by using those 2 points and the slope. But what we're going to be more interested in is finding the slope of a tangent line where we just have that single point and the slope that they give us. So there's a little green dotted line right here. What's the equation of that line? Or if we put that dotted line here, what would the equation of that line be? So let me redraw that stuff up, but with tangent lines instead of secant lines. So we are often interested in the graph and or equation of the tangent line to the curve at a single point. So to get the line, we got to know how to put things in point slope form and get slope intercept form out of it. So here's our basic parabola. Here's our x squared graph. Here is a tangent line at x equals 0. Here's a tangent line, if we call this x value 3. There's a tangent line. That is terribly written. I will do that again. At x equals 3. Maybe over here, this is -6. Here's our very steep tangent line at x equals -6. So again, very often we're interested in tangent lines to points on curves. The reason being, if we're talking about a small amount of time that's going to go on, just like a day or something, those lines can be used to predict what's about to happen. Will they be perfect? No. Are they a quick way of assessing what is close by? Yes. So again, tangent lines are often used for approximating a function value as long as we're close to where the tangent line is. So if I want to know what happens at 3.1, I could use the tangent value to get a good approximation. But I wouldn't want to use a tangent line at x equals 3 to predict what happens at x equals 20, because those are going to be very, very far removed. The quadratic graph would be very, very far away from that line by the time we make it to 20. It's okay at x equals 4. It's great at 3.1. It's kind of trash by the time you hit 2 units away for x squared. And that depends on the function that you're dealing with. Some functions, a tangent line is better for a longer amount of time. This gets into what we call numerical methods, where we start having computers do a lot of things for us. And your TI-83 actually does a lot of these types of calculations for function approximations. So I'm going to do these in a different order. Sorry, give me a second. More like 15 seconds, actually. Okay. Let's scroll. We are in example 2 now. Color. Find the equation. I could have typed that. Of the tangent line to the curve at the specific x value. So for A, we're going to have f of x be x squared. And let's do this at x equals 3. Now, we're not going to reinvent the wheel. From before, we know f prime of x is equal to 2x. I'm not going to do that limit definition for the derivative again, for the same one we've already done. Our function's x squared, we know the derivative. Again, this is the function that dictates the slope. Now, to find an equation of a line, you need 2 things. You need a point and you need a slope. So we need a point and a slope to make a line. The point, you just plug in x equals 3 to f of x. For the slope, you plug in 3, x equals 3, and 2f prime of x. You're going to plug the 3 into the function to find its y value. Then you plug the 3 into the derivative to find its slope. And yes, we already know that, but it's super short, so I'll show you the work. So f of 3, that's 3 squared, which is 9. So our point is 3, 9. That's our x1 and our y1. Now we plug the 3 into the derivative, which that function's 2 times 3, which is 6. That's our slope at the x value of 3. So at 3, 9, at that point, the slope is 6. It only has to be 6 at that singular point. So we have our slope, we have our point. This is our x1, our y1, and our m. So we just plug them into the point slope form. Y minus y1 equals m times x minus x1. Don't plug anything into x, don't plug anything into y. Just the x1, the y1, and the m. So again, I'll write that one last time, like so. So we get y minus, the y1 was 9, equals the m, which is 6, parentheses, then x minus the x value, which was 3. Then we take this and solve it for y to get it in y equals, which is slope-intercept form, and that's the best form of a line, most people would argue. So that's y minus 9 equals 6x minus 18, distributing that, adding 9 to both sides. Will give us y equals 6x minus 9. Oops, that's a 9. That is the tangent line at x equals 3. So if you graphed it, if this right here is 3 comma 9, oops, that was terrible. I hate this tablet. I know hate's a strong word, but I really don't like it. There's our tangent line, y equals 6x minus 9. So it touches at x equals 3 and x equals 3 only, necessarily. All right, we got about 10, 15 minutes. Let's do another one. That was example 2A. Let's do B. I am getting sick of that, so I'm just going to leave it in blue and red. Let's do f of x equals x cubed at x is equal to 1. So we need to plug that value into the function and its derivative. Now from before, we know f prime of x is 3x squared. We did that earlier, not going to reinvent the wheel. So f of 1, this will find the output. That's 1 cubed, which is 1. So our point is 1 comma 1. The x and the y values are symmetric, just there. The slope is f prime of 1, which is 3 times 1 squared, which is 3 times 1, which is 3. That's our m. So our tangent line is y minus y1, which is 1, equals m, which is 3, times x minus x1, which is also 1. Distribute the 3, you get y minus 1 equals 3x minus 3. Add 1 to both sides, you get y equals 3x minus 2. Watch your signed arithmetic. Your calculus students, you should know your signed arithmetic. I'm going to skip drawing this one. Feel free to do it on your own. C. Now, I will admit this one's going to be drastically more work. I'm actually thinking if we have enough time for that. I think we can. So f of x is equal to 1 over x. And let's do this at an x value four. And we are not actually going to finish this one tonight. This is where I had planned to end things, but I wanted to show you what the example was. Maybe you can find an example like it in your textbook or online if you'd like to just kind of take a peek at it ahead of time, because this one is going to be a little more complicated than what A and B were like. the process of actually finding the derivative just a little more complicated. So yeah, like I said, that's where we're going to stop things. I know I said like 10 or 15 minutes, but this was recorded for a different length of class, and I'm just kind of reusing it. So that's where we're going to leave things for the night. I do apologize for the part where it was muted. I knew that was coming up, and I just wanted to leave y'all in anticipation in the chat. I saw it popping up. I was like, I know it's only going to be like another minute. They'll be fine. They'll be fine. So like we said, we finished 1.1, 1.2, and 1.3 tonight. 1.1 and 1.2 had basically been finished before. So those are going to be due in a week on the 31st by 11:59 p.m. Don't forget to do that skills check quiz first. And then we started off the adventure in 1.4. So if you want to take a peek into those homework problems as well, be my guest, because since we're only doing this class once a week, it can feel like a lot and it can feel overwhelming if you wait till the last minute to do things. So please try not to do that. I know some people work really well racing at the finish line. And if that's you, if that's what you're going to do, that's what you're going to do. But you need to understand whether or not that's your personality or not. And if it's not, if you think it is, but it's not, maybe you need to reprioritize when you're getting your study and homework time in. But again, I hope we all learned some stuff tonight. We will learn more stuff tonight, more calculus, more stuff with derivatives, more topics with derivatives. We'll get into some really fun stuff continuing in chapter 1. And I might actually have a test date for you next time. I'm not promising yet. I'm trying to get things planned out as far ahead of time as I can. So let me see if I can do that just so you're prepared. Besides that, have a good week, have a good weekend, study hard, work hard, get good grades on your homework, and take care, everybody.